Hello, I'm Mike Griffith. I have an extensive background in rotary engines in North America. I worked for Curtiss-Wright, Outboard Marine, Johnson Evinrude, John Deere, AAI Textron, and Pat Power for the past 50 years, 1964 to 2012. I will use that experience to determine what the ultimate future of the rotary engine should be. There is still life in the rotary engine. The rotary engine is an internal combustion engine which utilizes a unique geometric motion to create a four-stroke combustion cycle: intake, compression, power, and exhaust, to produce rotary shaft power directly. This engine concept was introduced in the 60s and has been used for various applications since. A brief review of the rotary engine basic design serves to highlight its features and recognize that there are two basic configurations. The two configurations are differentiated by the rotor cooling technique, somewhat analogous to two- and four-stroke cycle piston engines. The air-cooled rotor is a simple and requires a fuel-oil mix for roller bearing lubrication. The oil-cooled rotor has conventional bearings and has high power capacity. Rotor cooling. The rotor can be air-cooled or oil-cooled. If the rotor is air-cooled, the induction charge must pass through the rotor to remove heat prior to entering the combustion chamber. The heat is carried into the combustion process but reduces the volumetric efficiency of the engine. The air must also contain a trace of oil to lubricate the bearings and be consumed in the combustion process, similar to two-stroke cycle engines. Oil-cooled rotors have a conventional unrestricted induction system but requires an oil system, heat exchanger, sump, circulating pump, seals, and pressurized bearings. Oil cooling produces higher power and more durability. Charge-cooled engines are the smallest, most compact design used primarily in non-motive automotive applications. The charge-cooled rotor engine uses side ports to get the flow through the rotor and then radial ports to guide the charge in and out of the combustion process. They are used in applications served by two-cycle engines. Engine cooling. Liquid cooling permits higher power but requires a heat exchanger and circulating system. Coolant is circulated through the rotor housing and side housings in series. This is the most common design. Air-cooled housings must have cast fins specifically concentrated in the combustion zone where the housing temperatures limit the power. Cooling is simpler, just needs a fan. An ambient air temperature rises, the power is further limited. Porting. For the induction and exhaust cycles, there are ports instead of mechanical valves. There are radial ports in the rotor housing, side ports in the side housings, and combined radial and side ports. Radial ports maximize uninterrupted flow but have excessive intake-exhaust overlap. Side intake and exhaust ports are more restrictive but greatly reduce the port overlap and emissions. Side intake and radial exhaust can be combined. The basic size, displacement, and geometry of the engine needs to be established even before deciding the design components. The geometry can be defined by the rotor radius, R, the rotor width, W, and the eccentric distance, E. The K factor, R over E, radius over eccentricity, is analogous to the bore-stroke ratio in piston terms. The displacement is calculated from the product of R times E times W. So W influences the length of the engine, much like the spacing of cylinders. The rotor completes the whole displacement cycle in 3 crank revolutions. The K-factor affects the external shape, the maximum compression ratio, and the angle of the apex seal to the truckoid surface. The diagram below demonstrates the influence of K on the geometry of the engine. Lower K factors represent a smaller, less complex engine. As it gets bigger, the compression ratio is smaller, but the bulk of the engine is larger. Because a major advantage of the rotary engine is size and weight, aluminum is the metal of choice for most housing components. The rotor housing is challenging because the combustion zone has high heat concentration and limited lubrication. The plain aluminum truckoid surface will chatter, so that various surfaces have been developed for durability. Thermal spraying, hard coatings, or a chrome-plated steel insert have been successful. The material of the apex seal has evolved over time to utilize several low-friction, low-mass configurations. The apex seal is a life-limiting feature for durability. It is spring-loaded to adjust for wear. Other seals depend on conventional piston ring technology because of the similar function in the application. The side seal to apex seal junction at the apex corner is one of the seal design patented by Felix Wankel to control the use of the engine concept. Side housings for air-cooled engines are cast aluminum with thin concentration on the hot zone like the rotor housings. They need a wear-resistant surface for durability. The thermal coatings and special aluminum alloys with wear-resistant properties keep weight down. Cast iron side housings have been employed for durability in applications with less sensitivity to weight. Rotors are cast iron for strength and durability. The casting has internal cores to minimize rotor weight because the weight must be offset by counterweights to eliminate vibration. Crankshafts and counterweights are all cast iron or steel. There is a planetary gear set with the spur gears stationary and the sun gear incorporated in the rotor. The indexing of the gears is critical, but the tooth load is insignificant. It is used only for generating the truckoid shape as the rotor orbits around the stationary gear and rotates on the crank eccentric. Let me transition from design to application. There have been various rotary engine designs. Starting with the late 1950s, NSU teamed with Wankel to issue licenses to their technology for the rotary engine. During the 1960s and 70s, the design garnered worldwide interest. Some of the major manufacturers are shown in the slide. In 1973, due to the simultaneous oil embargo and EPA emissions requirements, the automotive industry lost interest in the new engine technology in favor of improving their piston engine fuel economy and emissions. Since that time, the rotary engine developments have been very limited to just Mazda and a few drone engines. Permit me to offer a few personal comments. I worked at Curtiss-Wright on their multiple engine sizes and applications: aircraft, automotive, and military. They issued a sub-license to OMC, Outboard Marine, for North American recreation products. Many different sizes engines have been designed, including marine and model aircraft engines. I had the privilege of participating in OMC's rotary activities, specifically the outboard and the snowmobile engine. That's me with a 4-rotor racing engine on the dyno. All OMC engines had charge-cooled rotors. Most of the other licenses applications were for automotive use. Mazda, GM, and NSU all had oil-cooled rotors. Let me move from my past experience to my view of the future of the rotary engine. I would need to demonstrate a real cause for a new fossil fuel engine in a climate where such engines are declining in popularity and being supplanted by electric cars. The rotary is not widely utilized today, but has some basic features which are still applicable and may justify consideration because energy sources are shifting priority now that the global warming is an issue. Climate change and global warming combine to be a real motivator for the future. We must incorporate solar, wind, and hydroelectric energy as clean, renewable, and sustainable sources. Nuclear and geothermal, not so much, as they have significant limitations. These non-hydrocarbon sources address climate change and should be greatly expanded. Solar and wind have a gap caused by their limited availability, little or no wind or no sunshine at times. The gap must be bridged by other energy sources, primarily fossil fuel engines or engine gensets coupled with batteries, which will minimize the fuel consumption. Bridging the gap requires rethinking the most efficient ways to utilize fossil fuels in the future so as to minimize the effect on the environment and use as little non-renewable supply as necessary. An engine can be designed for optimizing fuel use by utilizing the inherent advantages of the engine in a genset configuration, programmed to maintain the batteries at optimum charge. The choice is piston or rotary. The rotary engine is simple, small, economical to produce, and can operate in a start-stop cycle, low NOx emissions, easily adapted to generators, and is known technology. Expanding each advantage will show how a rotary engine genset can be the bridge. Rotary engines are smaller than piston engines because the crankshaft is in the middle of the engine, collinear with the generator. The engine to generator requires no coupling. The smooth operation eliminates the need for vibration isolation. The high-speed capability of the engine means the generator will be small also. The generator set can operate on a start-stop cycle matched to the utility system demands. The Rotary is simpler than the equivalent piston engine because it has fewer, less complicated components. There's no need for connecting rods and valves to convert, reciprocating to rotary motion required to drive a generator. It uses ports in place of valves, eliminating the whole valve train. The lower component parts numbers minimizes the cost to tool for production. Fewer parts also means lower inventory for parts and ultimately lower production costs. Having a low-cost engine results in an affordable genset which permits wide distribution of the genset and battery to cover the energy gap in most utility systems. The NOx emissions of rotary engines are much less than the comparable piston engine because of the lower combustion temperatures and elongated combustion chamber. Designing the engine to run on just at one full power setting makes minimizing emissions and maximizing fuel efficiency while avoiding inefficient idle. The engine is not sensitive to detonation or pre-ignition, which allows production of lower-cost fuels distributed by existing infrastructures, including natural gas. The previous presentation of design and application of the rotary engine establishes the basis for the technology required for the new engine design. The future points to utilizing the rotary to supplant piston engines for gensets. The whole world has recognized the need to reduce fossil fuel use to protect the environment, but we are addicted to electrical energy. We need to rapidly develop new electric energy sources. The move to renewable energy is the future, but must incorporate a bridge technology. The Chinese government has committed to advancing the non-fossil fuel technology to improve the environment and establish a whole new approach to power generation. China has emerged as the world leader in adopting solar energy. They have developed the technology and applied it to reduce their dependency on fossil fuels and address the climate change. The progress in the last few years indicates an exponential growth in this new industry. China issued a summary report in 2018 that outlined their present status as a world leader and the commitment to accomplish their goals in a 6-phase plan. Quoting from the report, in 2018, China added 44 gigawatts of power, solar power. The increased total installed capacity by 34% compared to just the previous year. Wind power increased by 20 gigawatts, yielding a total installed capacity of 184 gigawatts. Their plans for 2019 continues to build technology for both their own future, but also as an industry for significant export possibilities. There are countries identified in their China's Silk Road vision to expand China's reach for continental markets. Africa countries are prime markets for new electrical technology and industrial productions. A portion of the letter from President Xi Jinping confirms the commitment. The chart from the report for the Chinese Energy Resource Institute shows future predictions emphasizing wind and solar as the energy sources for the future, which will displace coal for energy. The report points out limitations to achieving even higher solar and wind, meeting demands during periods of low wind and sun availability over extended periods of weeks or even seasons. The bridge for these gaps must be environmentally friendly. Sunshine is intermittent and wind is unpredictable. Both require a gap-bridging electrical source. This is where engine gensets, matched to battery storage units, can fill the gap in renewable generation. These gensets can replace large power plant installations and their attendant power distribution networks by locating near the end user application. The rotary engine can be designed to operate efficiently at a single design point matched to the generator and battery. It will optimize the minimum use of fossil fuels by operating intermittently only on demand. The new rotary engine design, an engine specifically designed for optimization at a single operating condition to either run efficiently at full power output or shut down if there is no demand. With this narrow design specification, a new rotary engine can be defined using direct fuel injection to replace the poor fuel economy of reputation of the past engines. I have always dreamed of designing an engine devoid of requirements for stable idle and good low-speed torque. Just start and run at full power. The generator design will be matched to the rotary engine shape and shaft attachment. The genset duty cycle, start-stop, should be tailored to optimize battery life by maintaining battery charge between 20 and 80%. Statistical analysis of electrical demands using more localized renewable resources will define a more efficient way to supply electricity to the community. Build the genset that will match most requirements to cover the electrical demands of the community. Low capital investment is required to tool and produce rotary engine gensets. The low production cost of these simple designs will allow proliferation of systems to maintain many new locations. Multiple gensets can be used to match demand over a broad range to be able to replace most large coal fuel plants and power distribution lines. If I have expanded your concept of electrical generation to accommodate the extensive implementation of renewable resources, please consider bridging the gap in power supply by using a new design of fossil fuel engines optimized for matching engine genset systems. That design will include the rotary engine with a unique advantage. I would like to end with a brief video of our Wankel type rotary engine, specifically the Mazda RX8 engine, Renesis engine, converted to run on diesel fuel, just to show the flexibility of this engine design. The video you will see is an RX8 engine converted by putting fuel injectors in where the spark plugs were, attaching a high-pressure fuel injection system, and incorporating the ignition system from the Curtiss-Wright concept of a stratified charge that proved that you can use heavy fuels in rotary engines. Here's the video.